Welcome back to our channel Machinery and Technology. Today we have a truly electrifying topic, the production process of hydroelectric turbine. The production process of a hydroelectric turbine involves several steps, from design and manufacturing to installation. Hydroelectric turbines are a key component of hydroelectric power generation system, converting the kinetic energy of flowing water into mechanical energy, which is then transformed into electrical energy by a generator. So if you are ready to spark your curiosity, let's dive right in. By the mid-19th century, water turbines were widely used to drive sawmills and textile mill equipment, often through a complex system of gears, shafts, and pulleys. After the widespread adoption of the steam engine, they did not, however, become a major factor in the power generation until the advent of the electric generator made hydroelectric power possible. The world's first hydroelectric central station was built in 1882 in Appleton, Wisconsin, only 3 years after Thomas Edison's invention of the light bulb. Its output of 12.5 kilowatts was used to light 2 paper mills and a house. Thereafter, hydroelectric power development spread rapidly, though even by 1910 most units delivered only a few hundreds of a few thousand kilowatts. Installations with more than a 100,000 kilowatts capacity were not built until the 1930s. One of the first large U.S. plants was installed at a Hoover Dam on the Colorado River between Nevada and Arizona. It began operating in 1936 and eventually included 70 Francis turbines, capable of delivering from 40,000 to 130,000 kilowatts of power, along with 3,000 kilowatts Pelton wheels. Water turbines are generally divided into two categories: impulse turbine, used for high heads of water, and low flow rates and reaction turbines, normally employed for heads below about 450 meters and moderate or high flow rates. These two classes include the main type in common use, namely the Pelton impulse turbine and the reaction turbines of the Francis, Propeller, Kaplan, and a Darius variety. Turbine can be arranged with either horizontal or more commonly vertical shafts. Wide design variation are possible with each type to meet the specific local hydraulic conductions. Today, most hydraulic turbines are used for generating electricity in hydroelectric installations. In an impulse turbine, the potential energy of the head of water is first converted into kinetic energy by discharging water through a carefully shaped nozzle. The jet discharged into air is directed onto curved buckets fixed on the runner to extract the water energy and convert it into useful work. If the electric load on the turbine changes, its power output must be rapidly adjusted to match the demand. This requires a change in the water flow rate to keep the generator's speed constant. The flow rate through each nozzle is controlled by the centrally located, carefully shaped spear or needle that slides forward or backward as controlled by the hydraulic servo motor. Proper needle design ensures that the velocity of the water leaving the nozzle remains essentially the same irrespective of the opening, assuring nearly constant efficiency over much of the operating range. It is not prudent to reduce the water flow suddenly to match a low decrease. This could lead to a destructive pressure surge in the supply pipeline or penstock. Such surges can be avoided by adding a temporary spill nozzle that opens while the main nozzle closes, or more commonly by partially inserting a deflector plate between the jet and the well, diverting and dissipating some of the energy while the needle is slowly closed. Reaction turbines. In a reaction turbine, forces driving the rotor are achieved by the reaction of an accelerating water flow in the runner while the pressure drops. The reaction principle can be observed in a rotary lawn sprinkler, where the emerging is drives the rotor in opposite direction. Due to the great variety of possible runner designs, reaction turbines can be used over a much larger range of heads and flow rates than impulse turbines. Reaction turbines typically have a spiral inlet casing that includes control gaps to regulate the water flow. In an inlet, a fraction of the potential energy of the water may be converted to the kinetic energy as the flow accelerates. The water energy is subsequently extracted into the rotor. There are, as noted above, for major kinds of reaction turbines is wide use the Kaplan, Francis, Darius, and a propeller type, in fixed blade propeller and adjustable blade Kaplan turbines. There is essentially an axial flow through the machine. The Francis and Darius type turbines use a mixed flow where the water enters radially inboard of the discharges axially. Runner blades on Francis and propeller turbines consist of the fixed blading, while in a Kaplan and Darius turbines the blades can be rotated about their axis, which is at right angles to the main shaft. Electric power generation. Water turbines are used almost exclusively for generating electric power that can be transmitted through high-voltage power lines to population centers. The United States and Canada are among the leaders in hydroelectric power production, though many other countries also have major production facilities. Until the late of 1950s, the most single turbogenerator units had capacity of less than 150,000 kilowatts. By the late of 1980s, construction costs and the need for reliability pointed towards 250,000 to 300,000 kilowatts units, although some recent installations were equipped with turbines capable of up to 750,000 kilowatts. Cost of hydroelectric power. Although large hydroelectric plants can be operated economically, the cost of land acquisition and of the dam and reservoir construction must be included in the total cost of power, since these outlays generally account for about half of the total initial cost. Most large plants serve multiple purposes: hydropower generation, flood control, storage and drinking water, and the impounding of water for irrigation. If the construction costs are properly proportioned to the non-power production utility of the unit, electricity can be sold very cheaply. In the Pacific Northwest region of the United States, such accounting has given hydroelectric plants an apparent cost advantage over fossil fuel units.